Okay, let's take a look at the class example problem, Unit A2, page 3. Here we go. The density of nitrogen contained in a tank is 1.5 kilogram per cubic meters. It looks like this is a density. When the temperature is 25 degrees C. Okay. Determine the gauge pressure of the gas if the atmospheric pressure is 97 kilopascal. Let's just take a look at it. Okay. We are going to begin with an assumption that nitrogen is an ideal gas. Under the given condition. So this is the assumption. If it's true, we can apply, of course, P equal to rho T. This is the equation of state for ideal gas. Okay, that's just to be very careful about that. When you use this equation, this pressure must be absolute pressure. You cannot use gauge. This temperature must be T absolute scale, not relative scale. Absolute scale temperature really means that either Rankine or Kelvin, not degrees F or degrees C. Okay, so having said that, first of all, we need to look into the property table, table 1.8. This is a handout given to you already. You can look up the gas constant of nitrogen. Which is 296.8 joule per kilogram K. This is the specific gas constant applied for nitrogen. So we need this data also to look up. Also, another thing, this problem is given atmospheric pressure, p-ATM. In this particular case, 97 kilopascal. Why do we need this kind of information? Well, we have to convert gauge pressure to atmospheric pressure, gauge pressure to absolute pressure through atmospheric pressure. P absolute is whatever the gauge pressure you measure plus p-ATM. Okay, we need this information. Okay. So let's just take a look at it. The situation here is, well, here is probably a sealed tank. With nitrogen filled. Now, condition given here is the temperature 25 degrees C of this gas. And then density is given 1.5 kilogram per cubic meters. Okay. The problem is asking you determine the gauge pressure of the gas. Gauge pressure really means that if this tank is equipped with pressure gauge, how much reading do you have? Okay. For a given condition of atmospheric pressure is 97 kilopascal. Now kilopascal is 1000 Pascal. Then Pascal is essentially Newton per meter squared. Let's be careful about that. So this is 97,000 Newton per meter squared. Okay, so we're going to apply P equal to rho RT straight out. P equal to rho RT. Now, important thing about it is here, once again, if you use this equation, pressure must be absolute, not the gauge pressure. Temperature must be absolute scale temperature. Okay, let's be careful about that. So P equal to rho RT, density is given 1.5 kilogram cubic meters. This is density. Gas constant we found for nitrogen 296.8 joule per kilogram. Okay. Alright. Then multiply by the temperature 25, but the 25 degrees C is not absolute scale. So you are going to add 273 to turn this into Kelvin. Okay. So you're going to pick up your calculator, punch those numbers in. The number you get is 132,670. It's a pretty big value. Now, what is the unit here? You are using density standard unit. This is all standard unit, by the way, joule. This is a Newton meter. And then Newton is, of course, kilogram meter per second square. Okay? So if you plug in all of those values with standard units, everything cancels out. The unit is essentially Newton per meter square. Now 1000 Newton per meter square is 1000 Pascal, which is kilopascal. So this is actually 132.67 kilopascal. But wait, this is not the answer. What kind of pressure this thing is? This is absolute pressure. That's not the problem it's asking you. Absolute pressure. Well, let's go back once again here. Since you're using absolute scale temperature, this is gas constant density. If you use P equal to rho RT, what you're going to get is absolute pressure here, of course. You have to convert absolute pressure into gauge pressure. Okay? How can we do that? We're going to use this equation. So, P gauge is equal to whatever the pressure you get, P absolute. Subtract P atmospheric. Okay? So let's do that. So P gauge, which is essentially the reading of the gauge pressure attached to the tank here, is 132.67 kilopascal. Subtract 97 kilopascal, which is equal to 35.67 kilopascal. This is what you need. This is called gauge pressure. This is essentially how much pressure value you are going to read from the gauge attached to this tank. Gauge pressure. Now, there's a few important things from this example. Let's imagine for yourself, okay, you're going to pick up a drill and then make a hole here for this tank. And what happens is, of course, the nitrogen escapes from the tank. Then gradually this supposed to be 75.6 kilopascal is going to be dropped down to 0. Right? So this actually introduces you the concept of zero gauge pressure. What is the zero gauge pressure? Well, that is the pressure essentially inside of this tank is equal to whatever the atmospheric pressure value surrounding this tank. So pressure inside and outside are essentially the same thing, there's no difference. So if you have a pressure gauge attached to the tank, it only shows zero gauge. So zero gauge pressure really means that the pressure is equal to local atmospheric pressure. I'm going to use the expression local atmospheric because atmospheric pressure may not necessarily be always this value. 97 kilopascal for this particular problem, but could be a different value. In fact, PATM depends on location and location mainly altitude. Altitude. So let me give you some examples. Typical value, usually called US standard atmospheric value. Okay. At the sea level, maybe Daytona Beach campus, PATM typically be 14.7 psi. Now Prescott is not sea level. Prescott is 5,000 feet. If so, PATM typically be 12.228 psi. Depends on the day, but this is very, very standard typical value. So PATM depends on location, especially altitude. That's why I keep using the term local atmospheric pressure. So if you are given information of local atmospheric pressure, you can determine gauge value. Well, gauge value is something you measure using pressure gauge. And then gauge pressure can only be converted to absolute pressure if you are given atmospheric pressure information. Okay? So that is something very, very important you can learn from this example problem. Okay, that's it.